Now we're going to get into what is probably the most complicated part of AP mechanics. Sorry guys. This is the kinetic energy of rotation. Up until now we have talked about the kinetic energy of linear motion. So an object that has a velocity, it's moving along. We know that the kinetic energy is equal to 1/2 mv squared. Hopefully that's still reviewed for you guys. The kinetic energy is equal to 1/2 mv squared. But we just talked about how we can relate linear motion to angular motion through the equation that the angular velocity multiplied by the radius gives us the linear velocity. So linear velocity is equal to r omega. V is the linear velocity, r is the radius of whatever kind of angle we're traversing, and omega is the angular velocity. Let's substitute this into our kinetic energy equation. So we have kinetic energy is equal to 1/2 m times omega r squared. We replace the linear velocity with r omega, and now we have to square that quantity. So now we're going to get that the kinetic energy is equal to 1/2 m r squared omega squared. Okay? This looks similar to our starting equation, 1/2 mv squared. This term right here is a little weird, but it looks like we have 1/2 some quantity multiplied by omega squared. And if you were thinking logically about this, you might assume, oh, okay, we're talking about angular motion that's going to be related to the angular velocity, so that's probably where the kinetic energy term is going to come from. Let's remember something here a little bit. Another word for mass, or another way of thinking about mass, is to think about it as the object's inertia. Okay? Inertia referring to the object's ability to maintain motion or resist a change in motion. More mass means that the object has more inertia. And up until now, we have considered every object to be a single point in space. Okay? So it's just been, even if it's been a box, it has been a box that has mass m, and we're only considering it a simple point. Okay? But now this term here is analogous to the term for inertia based on mass. So when we're dealing with rotation, m stands in for our inertia. Okay, it's going to resist the change in motion or try to maintain it. And now we're going to replace it with mr squared. mr squared. That term, mr squared, can be replaced with I. And I stands for the moment of inertia. The moment of inertia, I. It's the mass of the object multiplied by how far away it is from the axis of rotation. So R refers to the distance from wherever you're trying to rotate from. Okay? And now our kinetic energy becomes 1/2 I omega squared. This is the kinetic energy of rotation. 1/2 I omega squared. I is our rotational inertia, and omega is our angular velocity. So let's consider an example. Let's say that this is our axis of rotation, so some y-axis looks like our axis of rotation. I usually put a little kind of curly arrow to kind of let me know that that's where we're rotating around. And let's consider two masses some distance away from that axis of rotation. The first mass is going to be out here. It has a mass of 4 kilograms, and let's say it's a distance of 1 meter from the axis of rotation. The second mass is going to be a distance 2 meters from the axis of rotation, and it has a mass of 1 kilogram. And we want to solve for the kinetic energy of the rotation. We want to solve for the kinetic energy of rotation, but in order to do that, we got to get the rotational inertia for each object. So, misspoke a little bit. We want to get the rotational inertia for each object. Okay? The rotational inertia equation for a single point in space, is mr squared. mr squared. So the first one, for the 4 kilogram mass, is going to be equal to the mass, 4 kilograms, multiplied by the radius. That refers to how far away we are from the axis of rotation. This is going to be 1 meter squared. And so we get an answer of 4 kilogram meter squared. Okay? Rotational inertia has very odd units, kilogram meter squared. Don't worry too much about that. Okay? Now, the rotational inertia for the 1 kilogram object is equal to 1 kilogram multiplied. Now the distance is 2 meters, and that's equal to 4 kilogram meter squared. So we get the exact same rotational inertia for the two problems, okay? That's because this R term is squared. And you guys know this already. If you try to rotate certain objects rotate more easily than others if you think about the distance from where you're trying to rotate, okay? If you think about objects, rotate your pencil at your desk right now, rotate an eraser, it's easier to rotate some objects than others. There is now more than just a mass component to motion, okay? When we're talking about rotational motion, there is now an element related to how far away the axis of rotation is from the object, okay? Now this is all well and good until we start getting to objects that are not point-like, okay? So if we have some kind of object that, for example, we have the axis of rotation here, but let's say that we have a small, thin rod. Okay, we're going to have a small, thin rod. The rod has an overall length of L. So the rod length is L. The rod length is L, and it has mass, let's say big M. We're going to give us some symmetry on this problem to start. So we're going to say that the axis of rotation clean cuts through the rod. So we have L over 2 on one side, L over 2 on the other side. And now we want to figure out the rotational inertia of that rod, okay? For future reference, this is page 256. This example is on 256 if I go a little too fast here. Okay. Now since we have more than one mass, if we think about this as being made up of all sorts of different atoms inside here, all sorts of different masses at different points away from the axis of rotation, we have to integrate this guy. If you've already had calculus, you've probably done things like this before. So in order to find the rotational inertia, we have to integrate over r squared each individual mass term. Each individual mass term. So each small element of mass is going to be some distance away from the axis of rotation, and we have to integrate this entire thing. You have to integrate this entire thing. Now integrating over mass is pretty weird, okay? We're not going to do something like that. Instead what we're going to do is we're going to switch this into a distance integral. We want to integrate over distance rather than integrating over mass. So that way we can start at one side of the road with some x position and then move along the rod to the end with some x position, okay? So to do that, let's kind of do something that maybe looks at the density, kind of, sort of. So let's take the total mass of the rod, m, and divide it by the total length of the rod, L. That gives us something that's sort of like density, right? Mass over length, if you think about mass over volume, we're getting something that looks like density here. Now we're going to relate that, because that's now a ratio, that's going to be related to a small piece of the mass and some small length element dl. Some small length element dl. So this ratio needs to hold true. The total mass over the total length will then be related to some small mass element and some small length element. Okay? Now since we can imagine that this is our y-axis and the rod lies along the x-axis, we're going to replace dl with dx. Okay? This should kind of be a hint for where we're going here. We want to integrate over the x values. So instead of using dl, we're going to integrate from one side of the x-axis to the other. Now we're going to get that dm, so a little bit of substitution, bring the dx term up top here. dm is equal to m over L times dx. M over L times dx. This will allow us to substitute in this dm term into this integral term here, because remember, we don't want to integrate over mass, we want to integrate over length. We want to integrate over length. So now we're going to substitute that guy in there. R squared dm is now going to go to the integral of, clear that up a little bit. R squared dm is now going to go to, the rotational inertia is equal to the integral of x squared m over L dx. We're going to relate our distance away from the rotational axis as x, where some distance x to the left or to the right of the rotational axis. We have substituted in this m over L dx term for this dm term here. Now we've got to be careful about our limits of integration. Where are we stopping and ending the x term? Where are we stopping and ending the x term? I'm going to say that we're going to start over here at minus L over 2. If we consider this to be our y-axis cutting into our x-axis, then over here the maximum limit on this left-hand side is minus L over 2, and on the right-hand side is going to be L over 2. So our upper limit is going to be L over 2, one end of the rod, and our lower limit is going to be L over 2, the left-hand side of the rod. Okay? We integrate this guy. Integrate this guy. M over L comes out front because that's a constant. So we have M over L. L squared goes to L cubed over 3. L cubed over 3, excuse me, X cubed over 3. X cubed over 3. Sorry, misspoke. Thinking too fast. X squared goes to X cubed over 3. And our limits of integration, minus L over 2 to L over 2. A little bit of math here. M over L multiplied by, substitute in the upper limit, L cubed over 8 minus a minus L cubed over 8. I'll give you guys a chance to take a look at that. Substitute in the upper limit, M over L is still the same. Since we're substituting L over 2 inside here for X cubed, and I think I lost a 3. So I brought the m over L and the 3 out front, so I have m over 3L. X cubed now gets the L over 2 term, so that's going to be L over 2 cubed, that's L cubed over 8. Subtract the lower limit, which still has this minus sign out front, so now I get minus a minus L cubed over 8 again. And finally, I get that the rotational inertia is equal to mL squared over 12. mL squared over 12. Guys, don't worry too much about the integration here, okay? I know it's a little complicated, but don't worry too much about the integration. There's a lot of tricks that we're going to learn in the next video to kind of avoid this, okay? And if you look inside your book, you're actually going to see that you have a table in Chapter 10 that shows you a bunch of different rotational inertias, okay, for different types of objects. So spheres, hoops, rods at different ends. You don't have to worry so much about memorizing how to go through and solve one of these. On the AP, I really don't think they're going to ask you to do it. I haven't seen it looking back 15 years in AP exams. They never ask you to do it. Okay? They might ask you for a trick to solve for it, which I'm going to show you in the next video, but you will very rarely have to actually show how to do this. Okay?